Pikachu, let's get started, please. Today we're going to talk a little bit more about graphs, and then, as I mentioned last time, we're just going to talk about some random stuff in Python that needed to go somewhere, so we've put it into this lecture. So, first of all, I hopefully got the settings a bit better so that the labels are maybe a bit more readable. That doesn't matter so much today. So for today, what we're going to talk about is how is a graph represented. So how do you actually store a graph inside of the types of Python objects that we are used to? And one thing you can do is you can just get the list of edges from network X. And here's what it's printed out. It's printed out what looks to be kind of like a list of tuples. It says, well, there's an edge between 0 and 1. There's an edge between 0 and 2. There's an edge between 1 and 2, etc. So we're essentially just storing all the pairs that are connected to each other. And now we've basically stored the graph. I guess you might want to separately store the list of nodes. It could be redundant with this, but maybe you have a node that's not connected to anything, so maybe you also want to store the nodes separately. But this thing here is called an adjacency list. So if two nodes are connected, we sometimes say they're adjacent. So this is just a list of all the adjacencies. And another way you can store the graph is what's called an adjacency matrix. So what this is, and again, I just used the network X function to grab it. The adjacency matrix is a square matrix, in other words, a two-dimensional array. The number of rows is equal to the number of vertices. The number of columns is also equal to the number of vertices. It's a square matrix. And it just puts a 1 whenever there's a connection. So this first row here corresponds to node 0. And it's saying node 0 is not connected to node 0. It is connected to node 1. It is connected to node 2. It's not connected to node 3. And it's not connected to node 4. So you basically have a 1 indicating a connection and a 0 indicating no connection. So for example, if I wanted to say, is node 2 or is node 1 connected to node 3, I'd say node 1, 0, 1, 2, 3. Oh, there's a 1 here. So yes, node 1 is connected to node 3, but there's a 0 here, so node 1 is not connected to node 4. And notice how you have the same information in these two ways of storing the data. You have, they both just encode all the edges, but in a different way. So first of all, this matrix, the size is the number of vertices by number of vertices. And it's a pretty handy way of thinking about connectivity. So like I just said, if I want to just look something up, is 1 connected to 3, I can just look that up like I look up anything in a two-dimensional array, and I see a 1. So I see they're connected. And then the question is, well, how much space do these things take up? Because it kind of looks like the first one had a lot less information in it. The adjacency list was just O of E, where E is the number of edges. And in fact, the number of tuples was just exactly equal to the number of edges. Every time you had a new edge, you had a tuple, and you were just storing literally all the edges. Whereas this adjacency matrix has V rows and V columns, so it's a V by V matrix if V is the number of vertices. And so that's O of V squared. And the question is, which one is better? And well, this one looks like a whole lot more stuff than the other one. And indeed, it seems more wasteful because pretty much the most edges you could ever have is like V squared if everything is connected to everything else. But if you have fewer edges, then the adjacency list seems better. But what we would like to do is the kind of interface of the adjacency matrix is really nice. it's very convenient to be able to just look up, give me all the neighbors of node 5. Okay, I just take row 5. Boom. I have all the neighbors. Or is this connected to that? Okay, I just look something up. Great. So the question is, can we get something that feels like an adjacency matrix to us that we can access it in all these convenient ways, but isn't taking up massive amounts of storage? And the answer is a new data type that we haven't talked about before called sparse matrices. So let me just say, this goes well beyond graphs and connectivity. The definition of a sparse matrix in general is a matrix with a lot of zeros in it. And you could have a sparse vector. In general, this term sparse means the thing has a lot of zeros in it. That's really what it means. And it comes up in all kinds of different applications that you want to store something that is mostly zeros and just has a few non-zero elements here and there. So all the stuff we're going to talk about now isn't just for graph adjacency matrices. You're going to use it in other contexts too later in the program, but we're just introducing it in this way. Any questions before we go into the details? Yes, Derek.
So the matrix you showed us from the graph object, that would be relative to the order that you put the nodes in, right? Like that's not alphanumeric or ordered in any way. It's just however we put the nodes in.
Right. So the question is, what is the order? Yeah. So there has to be some implied order, and I think what's really happening here is that if I call g.nodes, this is the order that network X thinks the nodes are in, and so that's how the rows and columns correspond to the different nodes. But I guess I'm almost certain that whatever order those things were in when you asked to see the nodes is what corresponds to what.
So you just have to either remember or pull back.
Yes, correct. You just have to either remember or check. Yeah, Alistair.
So last class we talked about weights and directions with graphs. Could you also store those in this?
The question is, last class we talked about weighted graphs and directed graphs. Could you also start with this? So you could, if you had a directed graph, then the adjacency matrix would not be symmetric. So if you see here, it's a symmetric matrix, or if I the transpose of it is itself because it's symmetric, but a directed matrix might not have that property. And then if you had a weighted graph, you could have things other than 1 in there. So 0 could represent no connection, and then you could just stick the weight directly in it. Okay, so here's a graph. Here's the adjacency matrix that I got from network X, and now I'm going to ask Python what is the type. And the type is scipy.sparse.csr.csr matrix, whatever that thing means. We'll get into that a little bit, but the key is this is some new type that we haven't seen before that comes from scipy.sparse. So by default, network X is returning this sparse matrix data type, and that's exactly because it would be kind of a problem if you had a million vertices and it tried to return to you a million by a million NumPy array. There's just no way that's going to fit in memory if you have 10 to the 12 things. But maybe you have a million vertices, but you only have 5 million edges in total. So it shouldn't be that bad to store 5 million things. And that's where this sparse matrix comes in. So sparse matrices are both kind of an idea, like a dictionary is an idea and a set is an idea, but then the scipy sparse matrix is the one we use in Python. That's like a concrete implementation of this general idea of a sparse matrix. Going to this link. Is that going to work in full screen? Okay, so here is the documentation for scipy.sparse. And what you can see is that there's a whole bunch of different types of sparse matrices, and you can look into this more if you're interested in. You don't have to, but there's basically a whole bunch of them, and this one is a particular one called CSR matrix. And you can convert these to a NumPy array with 2array, and that's what I was doing earlier when I showed you that one earlier. So this thing is now a two-dimensional NumPy array because I called 2array on it. I think Tom showed you something similar in wrangling. You had a data frame and you did 2 NumPy or something like that. So this is a similar function that takes the sparse matrix. And it's usually a bad idea because it may cause you to run out of memory if you're dealing with a large matrix. Okay. Let's see. Where is this? Okay, so here I just made a random graph. This is just a built-in network. NetworkX has a bunch of pre-made graphs, sort of like R has a bunch of data sets that are already in R that you can just load them to play around with. NetworkX has some pre-made graphs. You can just load them to play around with them. So that's all I'm doing here with these weirdly named functions. I think this is a 100,000 vertex yeah, 100,000 vertex graph. I can get the adjacency matrix. I guess that's going to take a couple minutes. So when I call .shape, it's like the NumPy .shape. It's telling me conceptually it's 100,000 by 100,000 matrix, but it's not actually storing 10 to the 10 things on my laptop because those would mostly be 0. So a useful command here is NNZ, number of non-zero elements. And so what we can see here is that there's around 1 million non-zero elements. So what I'm going to get to here is that the sparse matrix basically just stores the non-zero elements and their locations in the array instead of storing the entire thing with all the zeros. So it's mainly just storing these million non-zero elements, which is the number of edges in this case, but that's way better than storing the 100,000 by 100,000 matrix, which would have 10 to the 10 entries in it. So yes, the full size, the full matrix would take up 80 gigabytes. So I guess you can get computers with 80 gigabytes of RAM these days. I think I probably have 8 or maybe even 4 gigabytes of RAM on this laptop. So if I were to store the whole thing, then it would be around 80 gigabytes. And by the way, we'll talk more about this in a later course, but we're operating under the assumption that each number we're storing takes around 8 bytes of RAM. So that's why I'm multiplying by 8. So what I'm doing here is I'm taking the product of this shape. The shape is 100,000 by 100,000, so I'm just multiplying those together. 100,000 times 100,000 times 8 bytes per number. And then I'm just dividing by 10 to the 9 to get it into gigabytes. So the sparse matrix, on the other hand, I can just ask it how many bytes it's taking. And it's taking up 7 megabytes. So the ratio of these is whatever that is, 10,000. So my whole point of showing you this is not so you can go through all those little pieces of code, but to say by storing this thing as a sparse matrix, it's 10,000 times smaller than by storing it as a dense matrix, and that is a big win. And the more zeros there are, the better it's going to be to just store the non-zero elements as a sparse matrix, and the more catastrophic it would be to actually try to store the whole adjacency matrix full of zeros. Just a second, Tom. So I'm guessing this will come up a few places in the program. One place I know it comes up is in the unsupervised learning course because I taught that course 1 year. So we mentioned earlier about nearest neighbors and Amazon products and similar items. So this comes up there where you have a bunch of Amazon products and a bunch of users who've rated them, and you get this giant table of all the items are the columns and all the users are the rows, and then you have the review that the user reviewed that item. But just imagine how sparse that matrix is. Like each user has probably reviewed a couple items out of millions of items, and so it's really mostly empty, that matrix. Most user item pairs, there's just no review available, and so it would be ridiculous to store that thing as a regular NumPy array, but by storing it as a sparse matrix, the amount of space it takes is pretty much just proportional to the number of reviews in total, which is actually pretty manageable. Oh.
For the sparse matrix, does it only save it as like a 0 or a 1, or can you have a larger than 1 value?
Yeah, you can have larger than 1 value. So it's basically 0 and non-zero. Yes. Your name again?
Akansha.
Akansha.
Adjacent matrix and the dense form of adjacent matrix.
Sorry, can you start again?
Are we interchangeably using the term dense form and adjacent matrix? Like once you referred it,
I see. I see. Okay, the question is, what do I mean by dense form? So by dense form, I'm referring to, scrolling up, I'm referring to this thing. So if I actually stored that thing as a two-dimensional NumPy array, that's what I mean by storing the dense form, because I'm literally densely storing every single number, as opposed to the sparse form where I'm only storing the non-zeros.
So when we say adjacent matrix, we automatically mean the dense form.
Well, that's the thing. Adjacency matrix is a conceptual idea. Like we have it in our mind that you have the vertices, and you say what vertices are connected to each other. But then how we take that conceptual idea and put it into a programming language like Python, that's an implementation question. And you could represent the adjacency matrix as a dense matrix, or you could represent the adjacency matrix as a sparse matrix. The latter would be a much better idea, but they could both work. Furkan.
Yeah, so my question is that how this sparse matrix compares in terms of build time and accessing time compared to lists and sets?
Yeah, the question is, how does this sparse matrix compare in terms of accessing time and build time compared to lists and sets? So we're going to talk about that a little bit later. But I'll say now, I guess, like one piece of good news is sparse matrices come up a lot. So the people who made SciPy put a lot of thought into making it reasonably fast. It's kind of like when we compared our set to Python set was just way faster because people had engineered it really effectively. So these are like hopefully good implementations of sparse matrices that should be pretty fast. Having said that, you have to be a bit more careful with them than usual, and we'll talk about that later. Other questions? Okay, so sparse matrices are for storing things with lots of zeros in them. That tends to come up a lot in practice, and it can save you, it can easily be the difference between being able to store it and not being able to store it. Actually, another, well, yeah, let's just keep going. Okay. Okay, we don't want to store the full matrix. Da, 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 da. Okay, so, yeah. So here I am, for example, just accessing row 0 of that adjacency matrix. And here's, it's printing it out to us in kind of a weird way. And again, it's because that's how it's storing things. So it's not storing that entire 100,000 row. It's still just storing the non-zero element. So this is saying at position 0, 2, 2, 1, 2, there's a 1. At position 0, da, 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 there's a 1. So again, yeah, this 1 could be some other number other than 1. But what this is telling me is that vertex 0 is connected to vertex 2, 2, 1, 2, and connected to 2, 4, 5, 9, 4, etc. So here's all the neighbors. But now we just need to talk about some syntax. So as usual with this course, there's a mix of ideas that are transferable to all kinds of programming languages, and then Python-specific stuff that is kind of annoying, but it just has to be done so we can get some fluency with these things in Python specifically. So here is a regular old NumPy array, just 10 by 10 random numbers. And I think we talked before, maybe in 5.11, that you can access an element like this in NumPy. If you have a 2D NumPy array, you can go x 1, 2. That gets me that particular element. And you can also do this in NumPy, x 1, 2. And here's what this means. In Python, I could kind of put parentheses here. This is what's really happening. The x1 is happening first. That's why I just put the parentheses to illustrate that. And then when it's done, the of 2 is happening afterwards. And so why does that work? It works because x1 by itself is actually valid syntax. If x is a two-dimensional NumPy array, x1 is just grabbing me the first row. And so if x1 is just grabbing me the first row, then x1 of 2 is getting me the second thing in this first row, which is exactly the same as just getting it directly like this. So I could have a temporary variable, and you can see I just retrieved the same value. So that's because conceptually a NumPy array is kind of like, a 2D NumPy array is kind of like an array of rows. And again, this is somewhat similar to what you're talking about in data wrangling with data frames. It's like, what was it, a dictionary of series or something like that? So this is a pretty similar idea with just a regular 2D NumPy array, is it's kind of like an array of rows-ish. And so x1 just gets me that first thing, which is that first row. Questions about this before we go on? Yeah, Derek.
Should x1 be the second row?
Sorry, yeah, second row. Yeah, thanks. Yeah, Furkan.
So what is the best, like, say, habit of?
Yeah, what is the best habit? Right, so this. So I recommend doing this. And one reason I recommend doing this is that when we go to a sparse matrix data type, so I'm just converting x to a sparse matrix, then this works fine. I get that same value, 0.319. But this throws an error. So this is like the kind of thing that just drives people totally insane when using sparse matrices, because, okay, those things both work in NumPy. Why do they not both work with SciPy sparse matrices? And I don't know why that design decision was made necessarily. Well, I could guess, but here's why. So when I just do the first part, the x sparse of 1, it actually returns to me, and again, this goes back to something we talked about before that's just a major nuisance with NumPy, which is that a one-dimensional array with 10 things in it is different than a two-dimensional array of size 1 by 10, even though in our brains those are the same thing, just like 10 numbers. But with the sparse matrix, when you do x of 1, it's returning something of shape 1 by 10 instead of just 10. And so then when I index into it again, it tries to index into that first dimension again, and it says, hey, that first dimension is only of length 1, but I tried to index. Yeah, Brendan's shaking his head. Yeah, it's annoying, but yeah, you need to know, because if you don't know, then you'll just get annoyed. So I think maybe this happens because the sparse matrix data type is all about matrices, meaning two-dimensional things, so it just likes to keep it two-dimensional. I don't know, or maybe there's other reasons for that, but just watch out for that. Make sure you know how you're indexing. So this is good for NumPy and sparse matrices, and in pandas you'll also have to be aware of the right way of indexing things. So just to make matters slightly worse for you, here's a list of lists. So with a list of lists, it's the other way around. And let me explain why it's the other way around instead of having you just memorize a bunch of things. So a list of lists is really, when I do LST of 0, I'm actually grabbing that first inner list. And then when I do of 1, I'm actually grabbing that element in the second list. Whereas here, the thing is, LST is just a list, and it's not really paying attention to what's inside of it. It could be a list of strings. It happens to be a list of lists. But in general, indexing 0, 1 isn't a reasonable thing to do for lists in general, because the stuff inside it might not be more lists. It might just be floats, right? So that just can't really make sense in general for lists, and so it throws an error. Whereas here, we're not really doing anything weird. We're just saying, give me the first inner list and then give me that second element. And so it prints out that 2 right there. So there is sort of a method to the madness, but it's also a bit frustrating. questions? At least, even if you lose track a bit of which is which, at least if you get these kind of errors, you could ask yourself, well, maybe I'm not indexing it right. Okay, sparse matrix operation. So let's try to find the vertex with the most neighbors. So actually, let me take a small digression here. So let's say let me just make a regular two-dimensional NumPy array filled with integers, nothing weird, no sparse matrix here. I just wanted to draw your attention to a pattern in NumPy. This came up in lab yesterday, and I think it's good for everyone to see. So if I call sum on x, it sums up the entire array. So 93 is the total of all of those integers in there. But if you look at the, yeah, right. So if you look at the signature for sum, there's this axis keyword. This axis keyword just shows up over and over and over again with NumPy related things. So if I sum with axis equals 0, x with axis equals 0, what it's actually doing is it's summing all the rows. So it's saying sum along the 0th axis, which is kind of the vertical direction. And so it's giving me the sum of each row. 2 plus 3 plus 2 plus 3 is 10, etc. And I can sum all the, sorry, here I summed all the columns by summing vertically. Here I'm summing all the rows by summing horizontally. So this is just a pattern that like tons and tons of NumPy functions have this. You know, mean, median, whatever. All these NumPy functions that you might use, they all have this axis keyword that says, if you don't specify the axis, just do it for all the numbers, but maybe you just want to do it row by row, or maybe you just want to do it column by column. So going back to the sparse matrices, I talked about, so here's this adjacency matrix, AM. You can get the number of non-zero elements. So this is, yeah, there's that many non-zero elements in the sparse matrix, but that same pattern from NumPy carries over to the SciPy sparse matrix. So I can shift tab here as well. And here I see this axis parameter again. So I can sum just along the vertical direction, or axis equals 1 and do just along the horizontal direction. But now it's just getting me the number of non-zero elements along that direction. So what's the number of non-zeros in the first column? 11. What's the number of non-zeros in the second column? 9. And that's handy because what that means is since we have a 1 when there's an edge from one vertex to another in the graph and a 0 when there's no edge, if we count the number of non-zeros along a column, or a row for that matter, then we're actually counting how many neighbors there are. And let me scroll back up to make that more clear. So scrolling up. So think back to here. If I can count the number of non-zero elements in the first row, then I see how many neighbors there are. There's 2. If I count the number of non-zero elements here, I see 1, 2, 3. That means there's 3 neighbors. So by performing that non-zero operation across all the rows, I get the number of neighbors. And likewise, I could do it for all the columns in this case because it's a symmetric matrix. In this particular case, you could also use sum instead of n and z because, well, you're just summing a bunch of 1s, which again counts how many things there are. But it's better to use number of non-zero in general because, yeah, you might have a weighted graph or something. Bronwyn.
I don't think we talked about vertices that have edges connecting themselves.
Yes. The question was, I don't think we talked about vertices that have edges connecting to themselves. So, yeah, we're just ignoring those for, I guess, most of the course. You will see such a thing later in the program, especially.
Adjacency matrix represents those as 2s, right? So
The adjacency
counting non-zero elements wouldn't get you the right.
That would be a 1 on the DAG.
Well, if the first node was connected to itself, you would have a 1 up in this upper left corner because this.
2.
Oh, it puts a 2 in there?
In the diagonal. Yeah.
Okay, I don't know. Yeah, so anyways, counting number of non-zeros should work if you count edges with yourself. There was another question, I thought? Okay, so this is an important idea here, that taking the number of non-zero elements in each row here gets us the number of neighbors for each vertex. And that's going to come up again, like with that Amazon data set I mentioned. If you want to know how many reviews did each user leave, you're, again, just doing that on the rows. And then you'll find out how many reviews each user left. Okay, let's find our way back here. Okay, so here's what I'm doing then. I'm doing number of non-zero. I guess, yeah, x is equals 0, x is equals 1, doesn't really matter, but maybe I'll just change it to 1. So I'm getting the number of non-zeros for each row, and now I have the number of neighbors for each node, and then I'm taking the argmax of that, which again tells me the index of the largest element. And I can also take the max instead of the argmax, which is just the value itself. So apparently, vertex the 37280 has the most neighbors, and it has 25 neighbors. Questions? Draco?
Yeah, so could you just re-explain why np dot, or like np dot sum x axis equals 0 and I can't read, am dot get, yeah, x is equals 0, you get two different results?
Oh, I see. That's just because the question is, why are these two getting different results? The NumPy thing, I was using x, which was just like a toy problem, and then I'm going back, so back to the adjacency equation. That's what you're asking?
Yeah, I just realized that you were using different.
Yeah, I switched between x and am just because I wanted to show this toy problem here.
Mike.
Oh, yes, Monique.
You glossed over this a little bit. You said they're symmetrical when you do it row or column. I don't really understand.
Yes, so since we have an undirected graph,
Yeah.
if vertex 3 is connected to vertex 2, then vertex 2 is connected to vertex 3. So if I'll just go back to it one more time. So if you look at, say, here it is, 0, 1, 2, 3, 2, like this,
Yeah.
3, 2 is going to be the same as 2, 3 because of that undirectedness of the graph. But in general, you could, of course, have a sparse matrix that was not symmetrical or wasn't even square. I mean, the matrix doesn't have to be square either, but just this particular case where it's an adjacency matrix of an undirected graph, it is both square and symmetric.
So for a directed graph, that would.
For a directed graph, it would still be square, but it wouldn't be symmetric. And then for some completely other application, like the Amazon thing where you had items and users, it wouldn't even be square because you might have a different number of items and users.
Makes sense. Thanks.
Carrie.
For a directed matrix, are the rows, is the standard of the row connected to the column?
Yeah, so the question is, for a directed graph, which convention do you use? I don't actually know what NetworkX uses. To me, it would be a bit more natural to have the rows be like the from and the, but you should check because it might not use that convention. Yeah. Okie dokie. So here's where we were. Regular NumPy functions do work on sparse matrices, but we have to be a bit careful. So, right. So here's the thing. The sparse matrices, another reason why they're a bit of a pain is because they're stored in memory, either row by row or column by column. So it's either stored like, here's all the stuff for entry 0, here's all the stuff for entry 1, here's all the stuff for entry 2, or they're kind of striped the other way in memory. So as a result, looping through the rows versus looping through the columns can actually take very different amounts of time. And this is like a particular nuisance, because with the regular 2D NumPy array, like you don't care, right? If you're doing stuff to the rows or doing stuff to the columns, you don't really have to think about these things. But with sparse matrices, so you have this CSR matrix. I'll just go back to the documentation. You have like the CSR matrix and the CSC matrix. And this is now kind of an advanced thing, but you actually have to be pretty careful about it, because conceptually they're both storing a matrix. Like the idea-wise they're the exact same thing, but they're actually stored differently, such that different operations are fast and different operations are slow. And I don't want to go into massive amounts of detail here because we don't have enough time, but I want you to at least be aware that the orientation of the matrix can change the amount of time it takes. So for example, this adjacency matrix, I'm going to just go through for I in range rows, and I'm just going to subset. I'm basically just grabbing that row. So I'm not actually doing anything with it, but I'm just saying, give me that row of the matrix, and maybe I would do something with it, sum it or whatever, and I'm just going to time it with time it. Okay, it takes 8 seconds. So the next thing is exactly the same, except I'm looping through the columns, and now I'm grabbing a particular column. So we've seen this notation before with NumPy, colon, comma, I would just grab a column, and with NumPy you wouldn't really make a big deal out of it, which one of these you're doing. But this thing is so slow, I can't even run it in front of you. That's why I had it commented out. So I just screenshotted the result when I ran it yesterday, which is that it took 12 minutes. So one thing is taking 8 seconds, and one thing is taking 12 minutes, just because you're looping through the rows of the columns. And again, it's because the way it's stored. It's stored as basically the first row, then the second row, then the third row. And so if you're just looping through the rows, it's very easy, because that's how it's stored. But when you're looping through the columns, so the first column says, give me column 0, it's having to go through every row and kind of search in that row for where is there any non-zero entries for column 0 in this row? Is there any non-zero entries for column 0 in this row? And so it's doing this whole complicated mess every time for every row to search within that row, and then it's horribly slow. So the way to deal with this problem is that you may, and again, this is a bit advanced, but you may need to switch between those types of sparse matrices. So with NumPy array, there was just NumPy array, end of story. With sparse matrix, you saw there was like 10 different types. So if I really needed to loop through the columns, I would actually switch it to a different type of sparse matrix, change the way it was stored, and then I could loop through the columns. It's the same data set, but just stored in a way that is optimized for a different type of access, and then hopefully it'll take the same amount of time as it took before. So gosh, there's a lot going on here, and I didn't really take the time to go into detail about how these things are stored and why and all those things, because there's just not enough time. But I really wanted you to be aware that this could happen, because sparse matrices show up all the time, and the difference between 8 seconds and 12 minutes is just like huge. So it's good to know these kind of things could happen, and if it happens, you could go and read about it and refresh your memory. And at least you'll have the idea that this could be the problem with your code being so slow. Sorry.
Yeah, I had a question. I didn't notice if you did run this to CSC now, or did you run it before? How much time does it take? Like,
oh, I just ran this now. Yeah, it was actually fast to convert it to the other type. Yes. Tani?
Would this be different from transposing the matrix and then just running through the rows again?
Right. Would this be different? So, okay, in this case, the matrix is symmetric, and so transposing it, that's kind of a special case. But if the matrix is not symmetric, you don't want to transpose it, because that changes in our mind, like you're changing the matrix.
I understand that, but this is, you've done this in order to run through the columns rather than the rows.
Yes.
But if I transpose it, the columns become the rows.
Yes, so in this particular case, you could do that. You could transpose it and go through the rows, but in general, you wouldn't want to do that because you're kind of then decoupling the matrix in your mind from the matrix in code. Because when you transpose it, you now have a different matrix and you'll just go crazy. So it's better to keep it the correct thing and just change the way it's stored. Okay, it's 10:10, so let's take a 5-minute break and resume at 10:15. The term sparse matrix is going to be a bit problematic because he was saying, well, I'm looking at that and that's a sparse matrix because the definition of sparse matrix is something with a lot of zeros. And that is true. So the word can be used differently. So conceptually, the word sparse just means there's a lot of zeros in it, and that has a lot of zeros in it, so it is sparse. But then this matrix could be stored as a sparse matrix data type in Python, or it could be stored as a regular NumPy array, which we're calling a dense or not sparse matrix. So that could be a bit confusing. Your conceptually sparse matrix may or may not be actually stored as the sparse matrix data type in Python. So that's a good point just to watch out for. Okay, where were we? Here we were. Okay, so okay, so sparse matrices come up a lot in practice. I talked about the Amazon thing. Came up in a capstone project. It comes up a lot in natural language processing. So a lot of times you'll have like 1 million documents and 1 million words in your dictionary, and you're just going to count how many times does each word appear in each document. And so now you have a giant matrix of number of documents by number of words. That's mostly zeros because a typical document is not going to have all the words in the dictionary, and it just maybe has 1,000 unique words or something like that. So I think you'll actually encounter that in the supervised learning course next block. But it really comes up quite a lot. Let's skip this. It's not that important. Okay, next thing, Python generators. So this next part is not related to graphs. It is just a Python thing that we need to talk about that we just completely didn't cover in the program last year, but then it came up in capstones and all sorts of things. So imagine you have to access a stream of data. Let me check the microphone's on. Yeah. Access a stream of data that you're just going to process one piece of the data at a time. And maybe the overall data set is too large to fit in memory. This is actually where it came up in capstone last year. Someone was training a neural network. The data couldn't fit in memory, and you needed to use a generator to feed in the data. So can we do that in Python? So here I'm just grabbing some list of words from some URL. And what I can do is use read line, which is some built-in Python thing that allows me to read one line of text at a time from some big thing of text. And I can just print out, I don't even know what this stuff is, just a bunch of words that are sitting in some file on someone's GitHub. But the point is, I can go through one line at a time rather than necessarily reading in some giant thing, and maybe that's going to work a lot better for me because I'm going to process one line at a time, and maybe I'm just summing the number of times I see the letter Z, and so all I have is some integer that's getting bigger and bigger and bigger, and I don't actually need the entire data set in memory at once to achieve my goal, and maybe the data set doesn't fit in memory, and so this sort of streaming thing is very important. That looks like the exact same thing, so I don't really need it again. Oh, but it has other stuff. Okay. Okay, I see. I have to do it again. Okay, so here's what I'm doing here. I have a list of vowels, and I'm reading each line, and I'm just counting what fraction of words start with a vowel. So, okay, I can run that code. And I see around 10% of words start with a vowel. You can look at this code in more detail later. It's not that important. But to figure out that 10% of words start with a vowel, again, I don't need to fit all of those words in memory at the same time. I can just check one word at a time. Does this start with a vowel? Does this start with a vowel? And so, yeah, there might be other things, like you might want to make a sequence, like 1, half, third, a quarter, etc. And you could make a Python function that makes that sequence. So it has a list, and it goes 1 over 1, 1 over 2, 1 over 3. But just like with the words, I can't take all the numbers from 1 to infinity because that's not going to fit in memory. But maybe I want to write my own function that the person can still ask for the next word or ask for the next number in this sequence, but not necessarily asking for everything all at once because that's just going to be too big and explode the person's computer. So this is kind of the goal here. We want to be able to write Python, create Python objects that conceptually correspond to the next thing and the next thing and the next thing and the next thing, but allow the user to just get the next thing one at a time instead of getting everything all at once. So that's the motivation for generators. And here's how it's going to work. We write a function with def just like we're creating a regular Python function, but all we do here is we replace the return statement with a yield statement. So as soon as you see a yield, that's basically what makes it a generator. And well, let's try it out. So run this code. And now it takes in a parameter n, so I'm going to call it with parameter 4, and we can see it's a generator object. And you may have encountered generator objects before, or maybe not. It's fine either way, but this is not exactly a function. It's something a bit different. And here's how I can use this generator. So I can actually, there's a built-in Python keyword called next that operates on these types of things. It just says, give me the next one. So now I can call next, and it gives me 1, and then I can call next again, and it gives me 0.5, and I can call it again here, and it gives me 1/3, and so on. So this is pretty bizarre because the generator is kind of remembering where it was. So it starts the for loop, it gets to yield, and then it just gives you that thing, and then it just kind of freezes. But it remembers where it was in that for loop, and then when you call next again, it kind of resumes operation until it hits yield again, yields you that thing, and then freezes. So that's very, very different from a function. Like when we call a function, it doesn't remember where it was when we do something to it and then do something to it again. Yeah, Reiko.
Is there a way to like reset it so you can go back?
Is there a way to reset it? So you could always run this code again, and now I just remade it, and it's going to be back at the beginning.
Okay.
So yeah, calling the generator again.
Is it like it never finishes?
Well, right. So in this particular case, it does finish because I've actually passed in n, which is 4, and the loop is only going up to 4. So if I call it, it at some point says, I don't have anything left. But I believe you should be able to make one with a while loop that would just keep yielding forever. Yeah.
Does it have a space complexity of 1 compared to the previous?
The space complexity, yeah. So it shouldn't be O of n. It should be like O of 1 in that I'm never actually storing all the numbers coming out of it. So yeah, that should be true, yes. Rock.
Can it also tell us where we are? Like,
can it tell us where we are? I don't know. Yeah. Kansha?
We can store these as a variable and use it in some other operations?
Yeah, for sure. So nums is a variable of type generator, but you could store the result of next in a variable as well.
So we can append them in a list and...
You could append them to a list, but that might be defeating the purpose of making it a generator in the first place, because the idea was kind of avoid having a list of all the numbers from 1 to a billion, because that was going to be too big, and I only need them one at a time anyway. So yeah, you could append them to lists, because that would be valid Python, but that's not really the spirit of what we're doing. Sir?
Does it only have to occur in the loops, the yield statement?
Say that again?
Like, can we state the yield statement outside the loop, and what does it do in this case?
Yeah, you should be able to put the yield statement outside the loop. So I think it'll just, yeah.
Yeah, but if you comment out the for loop and the yield in the for loop.
Okay, well then it's just only going to run once, so it's not very useful. So I'll run it the first. Oh, it'll even run 0 times? That's surprising. Oh no, yeah, it runs once and then it's toast. So basically, the first time you ask for next, it yields something, and then there's nothing under it, so it just errors out after that. Arun.
So the idea is basically to load like data in smaller chunks in memory, right?
Yes, the idea is that you can load data in smaller chunks in memory, yes.
Are there any other data structures, like generator has some limitations as we can see, right? So are there any other data structures which we can use?
Not off the top of my head, but yeah. I don't know, I don't have anything useful to say to that, so I'll just skip it, yeah, maybe. Yes, Rob?
Just on top of Serge's idea, if you add like I in front of I divided by 1 divided by I, yield I comma.
Then it's just going to be yielding a tuple every time.
Yeah, but I know which result is which, like the number. That's why I ask where.
Oh, I see, yeah. So you could do that to keep track of where you were. Yeah, that should work.
Is that an important thing to do or useful thing?
Not necessarily. Yeah, like with the words, like I just wanted the next word, and I was just going to keep going till I was done. So, I mean, if I scroll up here, like with this code, I basically just wanted to keep going until it ran out. I wanted to go through all the words, so I was just going to run this code. Well, okay, in this case, I happen to know how many words there were, but you can write a loop that basically goes until it runs out of things, which I'm going to show you right now. So let me do this again. Oh, I don't want that anymore. Okay, so yeah, so you can do this. So numbers generator 10 is going to get me that sequence up to 10, but then I can use this for syntax just like I do for element in a list. I can do for element in a generator, and it's just going to keep going till it runs out of stuff and not throw an error. So this is kind of the main pattern of where this is useful. So this just says, give me the next one at a time, and now if I wanted to like add up all those numbers, I could do something like that, and now this gives me the total of those first 10 numbers, but I never had to put 10 things in memory at the same time. I was just getting one at a time and adding it to the total, so I was only storing the current number and the total in memory. And this for loop thing, like I don't really need to keep track of where I am. As long as it loops through all of them, that's usually good enough. Karan.
Can you give any specific application where this can be useful? Because I'm not sure if I'm loading my data in chunks in my memory. So you don't have entire data set in memory. So if you don't have entire data from the zero cell, I cannot do anything on top of it. So where this will fit?
Yeah, the question is where this would fit. Like if I don't have all the data, I can't do anything with it. So that's not necessarily true. Going back to the words example, if I have 10 billion words and I want to know what fraction of words start with a vowel, like I had above, that is something I can do without the whole data set. Because basically I just get the words one at a time, and I'm just going to count. I have a total for how many words I've seen in total, and a total for how many words that I've seen that start with a vowel, and I just keep updating those totals, and then I can divide them at the end. And so I don't actually need to have the whole data set in memory at a given time. I just need to update some other things every time I see the next piece of data.
So it will be very use case specific.
Yeah, it will be specific. Like there's certain things you can't do unless you have all the data. I agree with that, but there's a surprising amount of stuff you can do when you don't have all the data. And if the data is too big to fit in memory, then you may need to do this kind of thing. Elliot.
Is that the main use for generators or for the yield statements in general?
It's the main use case for me for generator. I don't know, there's perhaps a universe out there of like other use cases. I mean, it's definitely about saving memory. Like, don't put it all in a list about saving memory, but then, I mean, there might be other things other than streams of data where you want to do that kind of thing. Okay, yeah, so the beauty is you don't really care if this thing in here is a list or a generator. You can just do for variable in blah, and all the code works exactly the same. So that's great. You can just swap it out, save memory potentially, and not have to worry about changing any of your code. So that's super convenient. Generator comprehensions. Okay, so in 5.11 we saw these comprehensions. Like this was a list comprehension, like a one-line creation of a list with a loop in it. We just talked about it very briefly in the last course. And then there was this ridiculous thing that when we changed the square brackets to the regular parentheses, you would expect this to now be a tuple comprehension because you make lists with square brackets, you make tuples with parentheses. And then when you change this comprehension, square brackets to a parentheses, it wasn't actually a tuple comprehension, it was a generator comprehension. So there's a lot of annoying inconsistencies like this in the language, but just FYI, that's kind of solving one mystery that we had lingering from a month ago or whatever, which is that this is a one-line generator. And I think range itself, by the way, is more or less a generator. I think range itself is not storing a list. So in an older version of Python, like 5 years ago, range would actually just give you a list, and then in the more recent versions of Python, range is a generator-esque object that just gets you the next integer and the next integer. But if you try to print it, yeah, it's not actually a list. Okay, it's basically a generator, even though it calls itself its own thing. Yeah, sorry.
If it's a generator, can we pass like infinity to it as an upper bound?
Maybe. Gosh. No. No, but I think you could have generators that will never terminate with the while loop or something like that. Okay, next thing. Map and reduce. So map reduce is kind of was or maybe still is like a buzzword about big data and that kind of thing. We're not going full on into it right now. We're just doing a more humble introduction to these things. And in particular, we're just going to talk about the literal Python map and the Python reduce, and just talk about what those things do. Again, it's just one of those things that we want you to see at some point in the course, and it doesn't really perfectly fit in with the spirit of graphs. Okay, so I think you will be seeing things similar to map and reduce in 5.11, the R part, and in data wrangling. So in data wrangling, have you had things like map or apply or something like that? Yeah, okay, I'm seeing nodding heads. So it's the same map that is sometimes also called apply. It's the same thing. So basically what it does is it maps or applies a function to a bunch of stuff. So here is a silly function called times 2 that just multiplies something by 2. Here's a list of 4 numbers. And if I map, if I map the function to the list, I used to get the results in the old version of Python, and I think I can force it to give me the results. Yeah, okay. I can force it to give me the results by explicitly saying, please be a list. By the way, speaking of that, you can also force range to give you the results by forcing it to be a list. But in newer versions of Python, for map and range and maybe other stuff, they've been moving towards this generator style, again, to potentially save you memory, just in case you happen to only need to go through them one at a time, and just in case the thing happens to be too big. So that's that. More recent versions, map returns what's basically a generator. So this is not going to work. This should throw an error because you cannot just get the second element of a generator. You have to get them one at a time, but we can still use next. Yeah. So I guess I should say that. I claimed range was basically a generator, so here's my proof. This hopefully works. It doesn't. It's basically a generator. But for map it really is. So next actually gets me the next one. So I could get 2, 4, 6, 8. Okay, so any questions about this? So map is a Python function that takes in a Python function. Again, that's something we briefly mentioned in 5.11, that you might pass a function into a function. So that's what I'm doing here. It's taking in a function and some data and applying or mapping that function to every element inside of data. Okay, yeah, I guess you've seen similar things in other courses. Oh, and here's the casting to a list that we already talked about. You may have seen per map, apply, pandas. Maybe the pandas one is coming later in your wrangling course. Right, okay. And so here I'm actually doing a map of a map. So how does this work? Well, the inner thing happens first. So this happens first and goes my 1, 2, 3, 4 to 2, 4, 6, 8. And then I'm taking that as my data and again mapping the times 2 function. So now I should get 4, 8, 12, 16. So I guess part of the point of this is that the second argument I'm passing to the outer map, which I've highlighted, is a generator-like object, but that's fine because map is happy to take that in instead of an actual list.
But will it have to execute the inner map, the whole, and store it somewhere?
Well, that's the thing. So the question is, will it have to execute the inner map and store it somewhere? So that's the thing. In this newer version of Python, the inner map is not actually storing it somewhere. It's just kind of a generator. And so it is only getting them as they need them. Elliot.
When you call lists, I don't quite understand how wrapping map and list converts it. Like, it would seem that you're calling list on a generator. Does that always tell list that, okay, you need to run this whole generator and convert?
Most likely, yeah. So in general, like as we saw before, if you call the name of the data type and give it something of a different data type, it's going to do its best to turn it into that data type. So it's doing its best to turn the thing into a list. That probably works for generators in general, but it's definitely working for this map object. It's just saying, okay, let me just next, and put them in a list. So the more, like, you could make a comprehension that would maybe be more clear, because we already know how the for loop behaves with generators. It just loops. So I could make a list comprehension out of that, and that is maybe more explicit. That's, I guess, what it's doing.
Sorry, Mike.
Yes, Rob.
Is that result still a generator? The last result?
This one?
The result, like.
Yes, so this result is still a map object, which is generator-like.
Can you try that? Because I tried it, it's giving an error to me.
Result. And then I could turn it into a list.
I mean, like, next result.
Oh.
Oh, sorry, something wrong.
No worries. Okay. Great. So yeah, we also talked about lambdas in 5.11. So you pretty often see lambdas in conjunction with map because you just need a little function and you stick it right in there. So here I'm just inline defining the function that multiplies stuff by 2, defining that right in the argument of map, and then passing in data. And that works as well. Did you do that in R, by the way? Did you have like an anonymous function? Okay, so same kind of thing. Questions? Gaurav?
Is it converting the inner map to a list and then mapping with the outer map?
Oh, up there. No, so it's not converting the inner map to a list. That's kind of the beauty of it, is that since I never told it to convert the inner map to a list, it's not. And since map accepts generators as its second argument, it just grabs them one at a time. Elliot.
Is there alternate syntax, like if you're chaining, like to chain these, if you have like 3 maps and then a reduce or something like that?
Is there alternate syntax to chain these? So I don't think so. I mean, are you thinking of the pipe maybe from R type thing? Yeah, so not really. There may be, so probably with pandas there is, that is panda's specific way of chaining with like this dot apply or map dot whatever, but with just base Python, for this example, I'm pretty sure you'd have to do it like this. Okay, reduce. So yes, I started by saying I'd talk about map and reduce. So I don't know, 1 or 2 years ago at some point, in the recent version of Python, they took reduce out of the standard Python that's already imported and made it so you have to actually import reduce yourself. So it's from some package called functools, which you don't have to install. It ships with Python, but it's just not imported by default. So you have to import this. And here's what reduce does. So here's again my data. And I could do things like summing my data, taking the max of my data. And what I'm doing is basically aggregating my data into a single thing in some way. And you could think of it as pairwise aggregation. So to sum those numbers, you could think of, I'm first summing 1 and 2 to get 3. Then I'm taking that result 3 and summing it with the next thing, 3 to get 6. Then I'm taking that result 6 and summing it with the next thing, 4 to get 10. Likewise with max, you could say I'm first taking the biggest of the first 2 things, 1 and 2. Okay, 2 is the biggest. Then taking the biggest of 2 with 3. Okay, 3 is the biggest, and so on. So you could think of both sum and max as doing a pairwise operation. And actually, on your lab 2, you were asked to write a recursive version of sum, and that's pretty much exactly what you were doing, right? You were taking the first thing plus the next. Oh, maybe it was the other way around. Oh, I guess it was still it was still adding things one at a time, just sort of backwards. So yeah, you could think of 1 plus 2 plus, I don't know where -5 came into play. That is now 4. Let's make it 4. Okay. You could think of it as 1 plus 2, and then plus 3, and then plus 4, and same with max. So here's what reduce does. Like map, reduce takes 2 arguments, a Python function and some data. So in that sense, map and reduce are the same. However, map, the function that you pass in, just is a function of 1 argument. So for example, multiply by 2. It just takes a single thing and multiplies it by 2, and then it applies that function to the first thing, to the second thing, to the third thing, to the fourth thing. Reduce is very different in that the function takes in 2 arguments. So the function you give to reduce, it has to combine stuff. So for example, I've given it lambda of x and y, x plus y. So I've given it a function that takes 2 things and adds them. It's combining them or aggregating them. And then I can call that on data, and it's basically summing the whole array in this way that I talked about. It's doing that function to the first 2 things, then doing that function to the result and the next thing, and doing that function to the result and the next thing, and so on. And I think I have a max example right below. Yeah, this is probably less helpful. This is just too much code at this point. But this function picks x if x is bigger than y, otherwise y. So in other words, it takes the bigger of the 2 things, and then I just apply that in the same kind of way. Gaurav.
You're passing 2 arguments, so these 2 arguments corresponds to the first and second data elements. Is it like that? And third?
Yes. Okay, so first of all, let's be clear here. Reduce takes 2 arguments, a function and some data, and then the function takes 2 arguments, which I'm calling x and y. But I think you're talking about the function takes 2 arguments. Yeah, so if I have 1, 2, 3, 4, then it's taking the first 2, 1 and 2, and doing that function to them, which is adding. So you could kind of think of it as, okay, this becomes 3, and all the rest of the data is still there from before, and then it's doing that function again and getting 6, and then it's doing that function again and getting 10, and then it's saying, okay, now I only have one thing, so I can just stop.
Like this, I can give any number of arguments to that function. Like lambda, I can give x, y, z.
No, this has to take 2 arguments, exactly. It's always just combining 2 things and doing that over and over again. Yes, Akansha.
Is there a specific reason why we are using a lambda function to reduce, or we are defining a very basic function with lambda? Like we could have written a lambda function which doubles the number.
Yes, there's no specific reason why I switched from a named function to a lambda, just, yeah, arbitrary. Yeah, Annie.
Having trouble getting the difference between map and reduce because both of them take in 2 arguments, function and data, and both of them do just apply the function to the data.
Okay, so the key, most clear difference is that if your data has n things in it, then map gives you back something else with n things in it. It's just modified each one of those n things by applying the function. Reduce, on the other hand, data starts with n things in it. It gives you one thing at the end, because it's iteratively aggregating things until you just have one thing left.
Thank you.
Brendan.
Is there a reason why we'd want to do it this way with the reduce rather than just calling the named function like you did in the rows above? Or is this just to illustrate that they're equivalent?
Yeah, there's no reason why you would want to do this as opposed to calling sum if you were just summing. But there might be some more complicated kind of aggregation you wanted to do where you wanted to be able to define the operation, and then you might do this. What's your name?
Luke.
Luke.
Is it possible to specify the reduce function to take 3 elements or 4 elements?
I don't think so. Yeah, the question is, can this function take 3 or 4 elements? I think it has to be 2. And it just does them one at a time. Okay, how much? We have 3 minutes left. Okay, conveniently, reduce can take in a generator, and so it can be coupled effectively with map. Okay, so here's where it gets a little complicated, but we can try to deconstruct this. So this thing happens first. It maps the doubling function to data. So the map is going to output a generator where each element has been doubled. And then that data becomes the data for reduce, which has the add thing. And so what this whole line of code should do is take 1, 2, 3, 4, double them all to 2, 4, 6, 8, and then add them all together and give you 20. Tiny.
We said map is basically a generator, which returns one thing at a time.
Uh-huh.
So it's calling on map twice every time, or the first time?
Sure, I guess so. Yeah, we don't really need to worry about those kinds of details. I mean, yeah, it can get the next thing as many times as it wants. So, I mean, the whole nice thing about generators is you don't really need to think about it too much. Just think about it as it behaves like a list 99% of the time, and then except it doesn't take up the memory. Okay. 2 minutes left. So let me just say that I have written a reduce function for you that we don't have time to look at. But it's not that hard to make your own reduce function recursively. So you can look at this later. It's actually pretty similar to the sum function you wrote in Lab 2, just more general, because it can apply any function, whereas your sum was specifically adding those 2 things together. So take a look at that. That might be a mistake. Maybe not. Okay. So yeah, I have my own reduce function. If you're interested, you can read the code. And in summary, map, also known as apply. So maybe this will help with Annie's question as well. So it takes a function of one argument and some type of thing you can iterate over and returns something of the same size with the function applied. Reduce takes a function of 2 arguments and a thing you can iterate over, and also known as aggregate, because basically aggregating everything into a single output by applying that thing over and over again. So I suspect you're going to see something in pandas very soon, if you haven't already, that has both the map flavor and the reduce flavor, but now you've seen the kind of base Python versions of these functions. So We're out of time, no time for true false, that's okay. I will see some of you in lab this afternoon, and I'll see the rest of you next week.